Environmental Design 3. We're going to cover various areas today. All the lectures I give are on Vital. We're also recording them on this thing, this screen capture thing. There's no need for you to write anything down particularly. No, but you have to stay in the room, obviously. But all you need to do is just take in what I'm saying, okay, and then get a feel for that. Then if you want to go back and revise it, the whole lecture is on Vital, and the audio of it is in here. Okay, so I shall make a start on what this is about. This is, in the previous years, the first year, the second year, the emphasis has tended to be on passive features of architectural environmental design. So it's passive solar, passive ventilation, daylighting and stuff like that. In the third year, we moved to the more sort of hard mechanical side of things, the artificial side of things. So I will talk for this week and next week about artificial lighting, electric lighting. And then a few other guys will come in and talk about other things as well. Oh, come on. Okay, so... Okay, so this is the syllabus for the course for the next 12 weeks or so. I am here now. There. I'm going to do the artificial lighting basic principles. Part of this is to remind you some stuff you have had in other parts of the course and introduce some new stuff. Although this is lamps and luminaires, I will do that next week. Our guest speaker, Michael Greaves, will come in and talk in the second lecture. So next week I'll talk about lamps and luminaires, I'll talk about basic lighting design, and I'll talk about lighting design case study using the example of lighting museums and art galleries, because that forms the basis of the assignment. For the few weeks after that, you get introduced to the guys from the acoustics group. The School of Architecture here has an acoustics research unit, which is one of the leading research units in the world for acoustics research. And you'll meet Carl Hopkins, Professor Carl Hopkins, who runs this module, and his colleague, Dr. Pyung Lee, or PLPJ as we all call him. They'll come in and do bits on acoustics. One of the biggest sources of environmental complaints in buildings is noise. Okay? It's not overheating, it's not too much light, too much light. The biggest cause of environmental complaints in buildings is noise. So we do a few lectures on stuff like that. Then finally, David Chow will come in, who most of you met in the second year, and he will talk about artificial heating and cooling systems, air conditioning, mechanical ventilation, that stuff like that. It's a funny semester because we do 10 weeks straight through. Then we break for the Easter vacation, and then there's only 2 weeks left when we get back, which is just pretty poor, really. So in week 11, the guys will come back and do a revision lecture to remind you all about it. And then week 12 is a bank holiday, it's a public holiday in the UK, so there will be no lectures here on Monday. So in effect, we're going to have really 10 weeks of teaching, then the vacation, then a revision lecture, and then we finish with this module, okay? The assessments for Arch 311, I know you're interested in this. What for my lighting, because, let's be honest, in the past, a lot of people used to fail this module. Right? It was a tough module. The acoustics is tough, the lighting was tough, the heating was tough. And because it's such a big variance, we thought, well, it's because it's all very techy and we're not doing anything to do with design. So a few years ago, we introduced this assignment, let's go back to it, this assignment here, which is what I will set to you. So next week I will talk about lighting of museums and art galleries, then the assignment for me is where you will go and look at a museum or art gallery, not just look at the things on the wall, but to look at the lighting. How does it use daylight? How does it use artificial light? What sort of lamps is it? Are there any problems with glare or dazzle? Can you safely move around the place without falling over or tripping over? You'll then produce for me an A3 poster. It says paper or electronic right now because SOTA only paperless submissions, but getting 220 paperless submissions on sort of Vital, and the aim to then look at them on the screen is just crap for me. So I'm trying to get them to submit paper. By next week I'll be able to tell you whether they've agreed to that or not. So one way or another you'll submit an A3 poster, which will be about the Walker Art Gallery, the Port Sunlight Gallery, some sort of gallery where you've gone in and looked at things, not at the exhibits, but at the lighting. Okay? You'll then submit that a few weeks later, 27th of February, and that will contribute 30% to your final mark. Okay, and because this is more of a design-based exercise, the idea is that you gather a lot of marks from that assignment, so that if things get a little bit wobbly in the written exam, then you've got enough to get over the line. Okay? So the second part of the assessment, I'm sorry, I'm going to be shaking. The second part of the assessment is a written exam. A written exam. And this will be based on the stuff that David Chow and PJ and Carl do on the acoustics and heating. So there's been no exam questions on the lighting. The lighting is all taken care of by the assessment. Okay? And obviously the written exam counts for 70% of the marks. We don't know when the exam is yet. It'll be in weeks 13, 14, 15. Okay, so that's the way it is. So in a few weeks we're going to do some making a poster describing the lighting event. What I'll do as well, because I'm such a nice guy, I will put some of last year's examples, some of last year's good, the bad, and the ugly of last year's examples, so you can see the sort of thing people do. Okay? That's nice, isn't it? Yeah? Thank you very much. Yeah. Has anyone got any questions about this so far? Any questions about this so far? Okay. Really?
So lighting won't be?
Sorry?
Lighting.
Lighting?
Yes.
What about it?
Will be in the exam?
No. Okay, no lighting, just acoustics and indoor climate. So there will be no questions from me. So this is what the lectures I'm going to do about, if I ever get around to them. One is how we describe light, one is how we make light, one is some of the basic lighting design principles, and the last thing is lighting museums and galleries, and that sort of segues, as people say now, into your assignment. Okay, so artificial lighting and sustainable design. It's very easy to think that sustainable design is all about insulation, photovoltaics on the roof, wind turbines in your garden and stuff. But lighting, getting the lighting right in a building, has a huge impact on its sustainable performance. So worldwide, electric lighting accounts for around 18, 19, 20% of all the electricity generated in the world is used to produce artificial lighting. And obviously it's still the case that most of that electricity is generated from fossil fuels, and therefore there's a huge impact of that. As I say, the amount of energy that we use, the electricity we use, the emissions from that, 1900 megatons of CO2, is equivalent to about 70% of all the planet's cars, the emissions from cars. So it's a big, big deal. Lighting accounts for about 15% of energy costs in the home, about 25% in commercial buildings, big open plan spaces with lots and lots of lamps in the ceiling. So it's a significant proportion of the energy budget of any building. Light is routinely supplied to places. We've got the equivalent here is when people started to get air conditioning and clever heating and cooling systems, then architects stopped wondering and bothering about climate design. They didn't start to design the window anymore to get lots of daylight in, or to get lots of solar gain in, or natural ventilation in. They knew that they could design the facade whichever way they liked, and then they could have a mechanical system which would heat or cool that space. And the same sort of thing happened with lighting. Once we started to get artificial lighting in spaces, and it was easy, it was powerful and controllable, then architects stopped worrying so much about window design and how to get the maximum amount of daylight into a space. Okay? So there's lots of spaces now, they're lit when they don't need to be because there's nobody there, or they are overlit. There's this idea that you make spaces very bright and vibrant by overlighting them. So we might only need a certain level of lighting to do the task in that space, but we'll put in that much lighting so as we go in and go, oh, wow, this is a dynamic space. Okay? And finally, of course, because if you don't need to worry about daylighting, you can make your building very, very deep plan. You know, those of you who were here in the first year, remember, I said to you really, if you have a window in a wall, you can only really get about 6 meters in before the effect of the daylight from that window disappears. And it's no good, it starts to appear a bit gloomy. So if you've got deep plan offices which is 30, 40, 50 meters deep, then it doesn't matter how big the windows are in the facade, they will never get enough daylight into the core, therefore you're always dependent on artificial lighting. Okay? So sustainable design involves sustainable lighting, and sustainable lighting ensures trying to get as much daylight into the space. Right? We all evolved as human beings under daylight, under sunlight. That's what our eyes are set to, that's what we work best on, that's what we feel most healthy with, and yet we stick ourselves in boxes where we are miles away from artificial. I mean, let's look at this lecture theatre as an example. Right? Anything could be happening outside. There could be a flood. Dinosaurs could be ripping up the campus as we speak. We wouldn't know anything about it because we're just isolated, and that's not so good. Okay, so as I say, you now lose the ability to design with daylight, which obviously up till the 19th century, when artificial lighting properly was invented, every designer had to sort of try and work with daylight to get maximum daylight into the space. the basic things we're trying to do with artificial lighting, obviously we need light for function, just as, whether it's writing, reading, sort of doing any sort of task. And we want that environment, that visual environment to be glare-free, stress-free, not give us headache, able to do our job easily. We need light for well-being. We have a circadian rhythm, we want to go to sleep at night, we want to wake up during the day. We have a circadian rhythm over 24 hours, and light triggers that. Okay, so if you're a night worker, if you're working night shifts, your whole circadian rhythm goes because you've lost touch with that 24-hour cycle of day and night. Light for emotional perception, obviously we go into a space and go, wow, this is lovely. And that's because the lighting is hitting the surface of that space, and we like what we see from that light that's reflected to us. Right? So creating these scenes and effects, these drama, an intimate atmosphere, if it's a bar or a restaurant, a clean clinical atmosphere, if it's a hospital, you create this with lighting. And as I say, finally, for sustainability, you're trying to balance the light quality with the energy use and integrating and controlling artificial and natural light. So you don't light spaces that are empty, you only light them when there's somebody there, and you try and get as much daylight into your space so that during daytime hours you're getting as much electricity-free lighting in your space as possible. So what is light? Well, light is basically just part of the electromagnetic spectrum. There's a spectrum which goes from sort of X-rays up here to radio waves up here. The size of these things go from like the size of football pitches, 100-meter wavelengths, down to millions, billions of a wavelength there. And light just happens to be just there. There's that one little bit of this huge spectrum from hundreds of meters to millionths of a meter, and this one little bit just triggers our sensation of light in our eye. And that seems weird when we've got such a wide range to do. Why would we do that? So light is just this spectrum. We have some red, orange, green, yellow, blue, indigo, violet. This very narrow band of range, about 480 to 780 nanometers, very small wavelength light. This is what stimulates our eye-brain system. Okay, and we have, because it goes about day and night, our eyes are adapted so that at one part of the day we can view in the bright daylight, and that's the photopic vision. When all the natural light is gone and we've just got dark, moonlight, starlight, we operate in a different part of the spectrum which is called the scotopic vision. Well, we're not bothered about colours anymore or fine detail, we're just bothered about survival, not tripping over something, not coming across a wild animal or something like that. Why did the human eye adapt to this range? Well, it's because if you look at the solar spectrum, which obviously brings all this light down to the planet, we see here that the solar spectrum has its most energy at that visible range, right? So it's not chance that we operate within this 480 to 780 nanometers. That's where the most energy is from the sun. So we as adaptive creatures have adapted to that. So it makes some sense. We don't want to be looking here at the infrared up here because there's hardly any energy in the sun. Okay. Vision, we interpret more than 80% of the information we receive from the physical world comes through our eyes. Right? We walk around space, we see people we know, we see cars and vehicles, we read stuff, we look at stuff. 80% comes from the eye. The physical world is captured by the eye. Light enters through the pupil here, gets focused on the back of the retina. The signals of the retina are converted, go down the optical nerve to the brain. The brain then interprets those signals to tell us, okay, oh, I recognise this person. I know what this task is. That is a danger. Okay, so the human eye basically consists of rods and cones. These are the light sensors at the back of the retina. These are colour-sensitive cones. These are black and white grey rods. This is what it looks like. If you look at the back here, you can see the rods are in green. They're called rods because they look like rods. And the cones are in blue. They're called cones, I don't think because they look like cones, but just because they look different to the rods, okay? So these are the receptors. The light comes in, the photons of light come in, these things pick them up, they then send the signals down to the brain, and the brain then thinks, okay, this is what I'm looking at. There's around 120 million rods, because obviously that's when you operate at night time. The rods kick in at night time when it's just all very dark, so you need lots and lots of these photosensors to try and pick up whatever information. During the day when it's sunlit, 6 to 7 million cones in the centre. They're colour sensitive, they give you different shades of colour and so on, whereas the rods just give you that sense of there's something there and I can see its colour. Okay, so we have this idea of night and day vision, and this change between night and day vision, it may seem very physically and techy, but actually we use it all the time in art gallery design and museum design. You're trying to create a dramatic sort of interior space. And so that normally can be quite dark. You go into this very dark space, you look at the exhibit, you go, oh, that's amazing. And then as you come out of it, you then come into a sunlit corridor. So you're moving between, in night and day, between scotopic and photopic vision. So you need to plan that, because as I say, there's a time delay in how you switch between these rods and cones, daytime and nighttime. So the rods do all this, they operate at night, the cones operate during the day and give us colour, the rods just black and white. The types of vision we get, well, normal vision is photopic vision, daytime, scotopic vision is nighttime, and then there's this messy one in between, the mesopic vision. Okay, and this is where, yeah, as I've said before in the first lectures, this is the time of the year, the time of the day when most car accidents happen. When lots and lots of accidents happen. Because the brain is trying to figure out, is it day or night? It's a transition time between day and night, and so the visual system does not work as efficiently. Okay, so in terms of driving at dawn or dusk, you misjudge the distances, you misjudge your speed, you misjudge the width of the road, the width of your car. This is when most accidents happen. So mesopic vision is a very sort of dangerous one. This idea of the eye adapting from dark to light and light to dark is called darkness adaptation. And as I say, if you see here, we have the cones on up here, that's fine, they're all doing their stuff. We then sort of go into a dark environment, the cones switch off and the rods switch in, and then the rods eventually get up and running. But look at the time, this is the time in minutes. So to switch from a light to a dark environment, and you know, you'll have all maybe done this, where you walk into, if you go from a well-lit space and you walk into a dark space, yeah, and then there may be a toilet at a restaurant or something, before you can find out where the light switch is, obviously you just lose all vision. You don't know where it is, your eyes don't adapt straight away. If you stood in that toilet for 5 or 10 minutes, obviously people wanting the toilet would be annoyed, but you would slowly start to adapt and see what was going on. And it's the same if you come out of a dark room immediately into daylight, what you do that, because your eyes are not going to be able to adapt quick enough, and so you get glare and dazzle and stuff. So this is one of the key things of good design, art galleries, cinemas, museums and so on, is that you will take allowance of the fact, and you'll see this time again, that when you do a good design in, say, a museum, and you go from a dark space to a light space, you'll find you don't just walk straight into the dark space. Okay, what you do is you come out of the dark space, it's a little bit lighter, but not much lighter. You then will quite often walk up a ramp, you then walk up another ramp, and this isn't because ramps are fun to walk on, this is because that's slowing you up and giving your eyes time to adapt to the lighter level. This is a bit of the easy bit of lecture for me. Eye-brain system, we think of the analogy between a camera and an eye. That a camera sees an object, records it on film or solid-state device now, whereas the eye sees an object and makes an impression on the retina and goes off to the brain. It's a false analogy because the camera will just record what it sees, the dog, the fish, the family member or so on. Whereas the eye brain is driven to make sense of it, based on experience of what's done before. The eye looks at it, the brain processes the signal and goes, what the hell is that? You know, what is that? And this is the basis of all these optical illusions, which I always love doing because I can take things easy for a little bit. So if you look at this, okay, this is a very familiar one. We all think there is a white triangle there. There isn't, is there? It's just that we've got notches cut out of these, but we think these are black circles. We think these two yellow lines are very different sizes, then we put the two lines in, and they're both exactly the same width. Okay? So there's nothing there, but the brain fills in and says, oh well, these look like they should be circles, they're not circles, so there must be a white thing overlaying them, because those lines are broken as well. Look at those two dots there. Those two dots are exactly the same size, aren't they? You say yes? Yes. Okay. We then put grey dots around them, and they appear to change size, because we are referring one to the other. Right? These big dots make this one look smaller, these small dots make this one look bigger. Okay? Okay, everybody feels sick, but you can go out now. But nothing is moving in that picture. Nothing is moving. Okay, here we see some purple dots going around in a circle. Everybody can see that. It's very difficult with the rake in the theatre. If you focus on that cross in the middle, just focus on that, just look on that. You should see the purple dots disappear. Yeah? They really shouldn't tell you to do this. Oh my God! Okay. This is what we always love. Watch that, children. This is obviously just a mass rotating round, but as it turns round to a certain way, the brain wants to make it seem like it's a mass facing us instead. So, oh no, it's just okay. I'm going to stop it now because okay, there are loads of those. So after that, so this is the brain is not just a receptor of stuff; it interprets stuff. That's what all those illusions are about. Let me just remind you about the units of light, because obviously just as we talk about temperature or decibels, we have to be able to describe light. So the four basic units of light in the environment. One is the luminous flux. That's easy. That's the amount of light that comes out of your light source, your bulb. Okay, the total amount of light that comes out, it's called luminous flux. The unit is called the lumen. Obviously, light flows in different directions. In this bulb, it's flowing in all sorts of directions evenly. If that was a spotlight, it would just flow out in one direction, and there'd be no light flowing in the other directions. So luminous intensity, the unit of the candela, that describes the way the light moves in a certain direction. Luminance is the most common unit of light we use, because this is the amount of light, luminous flux, that falls on a, what is that, surface? Hello? Surface, yeah? And so when you come to do design of an office, a school, an art gallery, they will normally talk about the task of luminance, and they'll say, well, you need 500 lux of light to do that. If you do very, very fine work, you maybe need 1,000 lux of light. So the amount of light lumens falling on a square metre of a surface is called the illuminance. Okay, so there's the illuminance there. And obviously the reflected light comes up into our eye, and that gives us the perception of the brightness of the surface, or what's called the lumen. I know a lot of these sound quite similar, but they're all slightly different units, okay? So flux is just the amount of light coming out of the light source. Luminance is luminous intensity, is the amount of light flowing in a certain direction. Illuminance is the amount of light you're shining onto a task, and the luminance is obviously how much of that light then comes back at you and gives you the appearance of brightness or something like that. So the lighting unit of flux is this, lumen. The symbol is these, we don't need to worry about that. Often included in lamp specification. So if we look at an order, yeah. What's that? Is the clicker still making its way around the building? Who's got the clicker now? Okay, good. That's brilliant. Keep going. It's fantastic. Okay, so if we look at something like this, we can say this Philips light bulb, it tells us 806 lumens of light will come out of that light bulb. Okay, we're not going to bother ourselves with lighting calculations because you don't need to, and it's just really boring. But you do need to, if you're a lighting engineer, you need to know how much light is coming out of your light source. So you need that information there, 806 lumens of light. And these are the sort of levels you get out of the old-fashioned 100-watt bulb. You get about 1,200 lumens of light coming out everything. A metal halide, the sort of thing they use in spotlights and in floodlights at sports stadia, you'll get maybe 200,000 lumens of light coming out. And what we see here is obviously this is the effects of different light sources and their energy efficiency. So you can see here the old-fashioned incandescent light bulb. To get 450 lumens of light out of an old-fashioned bulb, you need about 40 watts of electricity going in. Okay? To get 450 lumens of light out of a modern LED lamp, you need about 6 watts rather than 40 watts. So this is where the energy efficiency design comes in. You need to provide 40 watts of electricity to get 450 lumens, or you need to provide 6 watts of electricity to get 450 lumens. So this is why we've moved away from these and from these, to a certain extent these, and LEDs, light-emitting diodes, they now rule the world as the #1 light source. lighting units. Okay, so we're talking now about luminous intensity, the amount of light flowing in the space. And as we can imagine, if we switch this light bulb on, then whichever way we looked at it, we would see light coming out of it. But if we switch this light bulb on, if we are standing here and we look at it, we see no light coming at us. Its luminous intensity in this direction would be 0. Obviously, if we were stood underneath it, then the intensity would be very, very strong. So this idea that it's which way the light goes. And you're interested, well, you may be not interested, but the reason why we want to know it is because if you're doing an exhibit, you want to put a light bulb in, you want to shine it on a sculpture, a statue, and you want to be able to know which way it's going to light the statue, which way the direction. So it's useful to know which way the light is going to go. The unit is the candela, based on the candle. The symbol is L, and a candle, which is the basis of this, the name of it, the light you get off of a candle, the luminous intensity of a candle is 1 candela. Okay, so that's quite a quaint thing. 100 watt GLS bulb, it's 110 candela. The sun, 3 times 10 to the 27 candela, because the sun is very, very bright. Okay. The reason why, again, you need about luminous intensity, because it tells you where your light is going to go. So if you've got sort of a standard sort of fluorescent tube like this in a diffusing, reflecting sort of container, then most of the light will go down onto the work surface. And that's all in an office environment. You want to be sat at your workspace here. You want the light above, most of it to come down so you can do your task. Okay? But if you're trying to create an ambience, if you're trying to lift the ceiling to make it look light and floaty, then you might be more interested in having a nook lighter. And then obviously the luminous intensity there's none going down. This one, it's all going down just about. This one, it's all going up. Okay? So these are what are called polar charts, polar curves. And again, like with all the lectures we give on the environmental side, it's not that we're trying to make you into an environmental engineer, a lighting engineer, acoustic engineer. What we're doing is trying to give you some of the vocabulary, some of the terms, so that when you're on your big job, when you are designing that fantastic gallery, then you can talk to the lighting engineer, and when the lighting engineer says, well, actually, we need the light intensity to be mainly on that, you understand what he or she is saying, that you understand the terminology, you've got the vocabulary. Okay, next lighting is the illuminance. I say this is the main one. The amount of light shining on the surface. Units is called the lux, and this is the one you'll see time and again for task lighting. You'll see there 500 lux, 1,000 lux, 2,000 lux, and so on. Symbol is E for some reason. 1 lux is 1 lumen of light shining on 1 square metre of surface. It's dependent on the direction from which the luminous flux reaches you. As I say, depending on, you've got lots of light coming down from a light source. If most light is going up onto the ceiling, the amount of light of the luminance on your desk will be very, very small. So it all depends on the lamp, the optical design, the luminaire, the shape of the housing which you put the lamp, which I'll talk about next week. And typically, if you're in a field under a bright sunny day, you'll get about 100,000 lux of light shining on you. If you're in a building, you'll get about somewhere between 500 and 1,000 lux of light. If you're in moonlight, under a moonlight sky, then you get about 100 units of light or 100 lux. Okay? So typically in most buildings or most situations, somewhere between 500 and 1,000 lux will enable you to do most of the tasks you would do on your screen, reading a book or whatever. But the final one is luminance, which in effect is what we perceive to be the brightness of the surface. The unit is the candela per square metre. And that's just basically how much brightness is coming up per square metre that you can see at the surface. The symbol is L, and it's how we perceive the brightness of a surface, the luminance. Okay, and if we look at the surface of the sun, again, which is very, very bright, so it's a very big number, 1.6 billion candelas per square metre of area there. We come down to office desk, it's got a luminance of about 100 candelas per square metre. We come down to a road surface street lighting, 0.5 to 2, just enough to enable us to get on with the task. Okay. In terms of visual performance, because this is what I say, you're designing these spaces, they have to be safe. Visual performance, our ability to see things, to do tasks, to appreciate things, an artwork, a book, whatever it is affected by the size of the task detail. Right? Obviously, we go for an eye test, and we know that this one's normally easier to see than these ones. The smaller ones are harder to see. Our visual performance is much poorer the smaller the task. The contrast of the task, how it stands, the contrast, the darkness, if you like, of the task compared to its background, that's the contrast. The luminous brightness or luminance flux density, how much light is going on compared to how much light comes off. If we have a very luminous surface, we get a lot of light coming at us, so we have to be able to do a good task. If it's a very dark surface, we don't get much light back, so we can't do the task as well. Disability glare, sometimes if you have a light source which is like causing you to do this, or even if you have the sun coming through a low sun in winter, or a light source which has not been shielded properly, it can cause glare. Glare means you can't do the task as well. Disability glare, just glare, as we say in Liverpool, glare. The thing about how long you've got to look at the task, right? If I put something up saying, okay, read this, okay, what did it say? Then you probably may not be able to read it very quickly. If I pick it up and say, what does it say? And I give you 5 minutes, you'll be able to read it. So these are all the things that affect the visual performance, how people perform in the areas that you design. Chromaticity, contrast as well, this is to do with colour contrast. Can everybody see a number in there? Is anybody who can't see a number in there? No? Because if you can't see a number, then you are colourblind. That's a standard test for colour blindness. Okay, so everyone should be able to see the number 46 in there, is that right? It's a 12. Okay. Also, sadly, age as well. Like all things, a car with 20,000 miles on it is not as good, is better than a car with 60,000 miles on. And the eye is equipment. It gets older, it gets clouded, sort of gets all things cloudy on it, and so on. These are all things that affect visual performance. But unlike a lot of things in life, it's not a question of the more light you put on a task, the better your performance. Okay? And this is one of the reasons why when people had free access to high-powered light, and they used to put 2,000, 3,000 lux in an office environment, you didn't need it. Because this is the way you and I perform visually. Okay, obviously if there's no light at all, we perform pretty badly, but as we increase the light, our performance improves, we can read things better, we can do things better. But we then go to a certain level, and actually, it doesn't make us get any better. We don't read quicker, we can't type better, anything like that. So we have this plateau effect. And then actually, if you get too much light, there's always the risk you're going to get glare and dazzle and stuff, so our performance actually starts to go down again. So obviously, in a good lighting design, a good energy-efficient, sustainable lighting design, are we all done? Yes. Okay, thank you very much for doing that. Okay. Where is the rose of shame start? Okay, so as I say, in a good lighting design, obviously you want to get your lighting level. What is that? You're just about there. Okay, that's because if you put twice as much light in, you don't get any benefit. You just get a bigger electricity bill for your lighting. The relative importance of visual factors, if you increase the size of an object by 2, that's the equivalent to increasing its contrast, the difference between foreground and background by 6, or to increase the luminance by a factor of 100. Okay? So you've got a task that you do. You can either say, okay, people have to read this. Be good if I had a thing here to write this. People have to read this. Okay? And if people think, well, maybe they can't read that, okay, I'll increase the amount of light on this. Is this one of these ones I can rub off, do you think? Okay, so I do a little thing like this. Right? And you say, okay, that's not very good, so you put more light on it so I can see it. But if I make it twice as big, because that's what it was, if I make it twice as big, then you can see it more easily without needing any more light on it, okay? So increasing the size of an object is all important. Improving the visibility, you can see basically as we go up here, things get easier to read. Contrast, the difference between the foreground and the background. Obviously, it's much easier to read that as contrast than it is to read that as contrast. Okay, so here we see a typical sort of eye test here. Okay, so very easy to see when the contrast is strong. Much more difficult to see when the contrast is weak. So improving the visual performance, improving the appearance, contrast size. And I say what people sometimes do is they put extra illuminance on it, they put more light on, but really they need more contrast or they just need to make the thing bigger. Okay, so we'll do a summary of the lecture. I'm going to finish it a little bit early, I think, so I can go and get the guests for the second one, so we can have a bit of a rest. It's very warm in here. We perceive the world mainly through vision, so actually good lighting design is really important for all sorts of reasons. Obviously, we perceive architecture through light, through vision. Okay, we don't tend to smell it, We maybe hear it a little bit, but we tend to appreciate architecture through the light that is reflected off our light architectural surfaces. Okay? And obviously our interaction with people, our performance of tasks, depend on vision. Lighting can play a huge role in sustainable design. Basically, if you've got a 1970s office block and it's got old light lamps in, okay? And as I say, you may think about, well, let's put triple glazing in, let's put photovoltaics on the roof to save some energy. They will save you 5, 10, 15% energy. But if you go through that whole 70s tower block and you replace every of the old fluorescent lamps with brand new LEDs, you will probably reduce your energy savings by about 75% in that building. The changes are absolutely enormous for getting the lighting right. So obviously there are other issues to do with things like, fluorescent lamps contain mercury. Mercury is a very nasty substance for the environment. Other sorts of lamps have sodium in. Again, that's a very caustic thing. So if we just throw, as I'm afraid maybe some of us have done, if we just throw our compact fluorescent bulbs in the bin, there's always a chance that that lamp will be broken, the mercury will get out and then start to contaminate either the ground it's been buried in or the air that's surrounding it. There's other issues now which you may come across in your design careers of light pollution. You know, people are really bothered now about the fact that we put all these lights everywhere. We have office buildings which are lit at night. They produce huge amounts of, obviously if you walk around Liverpool, you look at office buildings that they are glowing with light. That is all light coming into the environment. We would prefer to have dark skies, a lot less light pollution. So sustainable design is one way in which you can do that by reducing the amount of light in the space. Okay, I say less lamps, more efficient lamps, less electricity, less fossil fuel, less CO2 emissions. Yeah, although it doesn't seem a particularly sexy subject, getting the lighting right not only gives you a very nice environment and enables you to do all the tasks, it has a big impact on sustainable design as well. Visual mechanisms differ with light levels and times of day. This photopic and scotopic thing. So you have to allow for that in your design. You allow for that time thing about how people adapt from light to dark and dark to light. You design your spaces so that they're not people at risk. Sort of things you never do is you never have a light from a dark space into a light space where there's immediately stairs there. Okay, because people will just walk out, not be able to see, and they'll fall down the stairs. Okay, so that's why you have ramps in museums rather than stairs. Visual performances is complex mix. It's not just one thing. It's contrast, it's size, it's illuminance, it's the age of your eye, it's the time you've got to look at the task. All of these things together contribute to you being able to do. I mean, it sounds very dry to a visual performance, but a visual performance is reading a book, looking at a piece of artwork, looking at your phone. All of these things are visual performance. Good lighting design considers all of these factors that interact together. And obviously what you're trying to do is perform a building which will work from a task point of view. You can do the things, whether it's a gymnasium, a library, whatever. You can do the task in that building. But at the same time, you're trying to use the lighting to create a nice aesthetic. It seems like a nice space to be doing that particular task. Okay, so that's the end of the lecture. Has anybody got any questions about anything? Well, obviously, anything to do with the lecture, not anything. Where is the clicker thingy scanny thing? Are we nearly done with that? Yeah? Are we nearly done with that? Oh, come on. Are you eating it? Don't eat it. That's wrong. Move along. Oh, sorry, I thought that was just your hair. Sorry. You're a long way back. Yes?
Yeah, just wondering, are there lighting systems which allow the circadian rhythm so they change from blue to red light in the course of the day?
A very good question. Yes. Because of the circadian rhythm, obviously, I'll talk about this in the next lecture, but basically, obviously, the colour of light changes. The idea of colour of light seems strange. But obviously you can get a cool light, you can get a warm light, and this will affect our thing. And at different times of the day, obviously in the middle of the day, the sun's quite bright and strong. The other parts of the day, it seems the light level's a lot lower. So this idea, if you are trying to, you know there's a thing called SAD, seasonally affected disorder, particularly in high latitude countries in Scandinavia, where it's dark for a lot of the year, people need to get to entrain their circadian rhythm, they need light. And what they sit in front of are lamps which have a full daylight spectrum. So they cover all of these things. They cover the blue part of the day and the red part of the day, the sunrise, the middle of the day, the sunset. And people in offices at high latitude sites will sit in front of a lamp on their desk and just let their brain take in the fact that even though it's dark outside because it's the middle of the winter and the sun hasn't risen above the horizon, they kid their brain into thinking this is day. So that when they go to bed at night, they can sleep. They're not thinking that they've been up all night because it's been dark outside. So these what are called full spectrum lamps, which have equal distributions of blue, red, orange, green, yellow, and all the rest of it, they are what you use at high latitude sites to try and just keep going this circadian rhythm. Yeah, so it does happen. What's called full spectrum daylight lamps now are what people use to do that. Good question. Any other questions for anybody right now? About anything, the scheme, the assignment. I put this lecture on Vital now. Our guest speaker Michael Greaves is going to talk a little bit about energy efficiency in general. I'll see if he'll give me his lecture. Next week we'll talk about lamps and the scheme and lighting museums and art galleries. Okay, if you want to get out now for 10 minutes, then that's great. If you come back at 3 o'clock, then we'll have the guest lecture from Michael, and then we'll be done for the day. Okay, thank you very much for your patience and your discussion with us.